So we're going to talk about machine learning, and in particular, we're going to talk about scaled machine learning. So, well, I'm Reza Zadeh. I'm a consulting faculty here, and I'm founder CEO of Matroid. I also advise Microsoft and Databricks, so full disclosure, those are my biases. So a machine learning pipeline typically looks like this. There's always some data, and that gets fed into a learning algorithm. The learning algorithm trains a model. That model is then sitting somewhere which can be replicated. So we can then replicate the model and have it served all over the place, whether it be on your phone, looking at pictures that you've taken, or trying to figure out what you've said, or in a web server somewhere acting on your clicks and your behavior on a website, or in your car trying to help you drive your car. That model has been replicated all over the place. And often that model is so valuable to you that you want to use it a lot. You've built it so that you can automatically use it, and therefore you want to use it in a lot of places. You want to serve it in many places. So this is a typical machine learning pipeline. And actually, almost every single text box here benefits from being scaled. So we care about feeding our algorithms more and more data because they happen to learn more and more interesting things the more we feed them. So we need to scale this part. Learning algorithms will have to change as we put 1,000 machines together to train a model. And so the whole learning algorithm has to be redone and refactored. Once you have a trained model, you can start asking, well, how big should my model be? Actually, it's a kind of an unintuitive thing. At first, you might think, well, I want to take my data and I want to compress it into some tiny, small model so that generalizes. But we've observed that also large models help us model complex problems quite efficiently without having to think too hard about modeling, without having to think too hard about putting our own smarts into the model. So it's a little bit of laziness on our behalf that we want large models, but nevertheless, they help push the field forward. And then replicating model and serving the model should be obvious. That's just, you want to use your model all over the place. Now, every single one of these parts needs to be scaled, and the way that we scale things these days is by putting together many machines. And that's largely because CPUs have stopped becoming faster and faster, so the way we get throughput and the way we manage lots and lots of data is by putting together many machines. There's some fundamental physical limits in how fast a CPU can be. So we take machines that have commodity GPUs, commodity CPUs. These are things you can buy off the shelf, connect them together with Ethernet, cables that you can buy from Target or Fry's, and we hook those together, and now we have to build smart software to actually manage these thousands of machines that we've hooked up together. And you can now rent these machines off of Amazon, Microsoft, Google, all these cloud providers rent you machines. The question is, though, as software engineers, as algorithm designers, and as mathematical modelers, how do we deal with our algorithms getting thrown out the door and being replaced by things that have to run on 1,000 machines? So the question is, how do we program these things? And some of the challenges that we have to solve when dealing with 1,000 machines are quite difficult for a person who doesn't have a sort of a hardcore computer science and systems background. These problems there are many. I'm just listing a few. The first one is, how do you ship your computation to your data? Often you have so much data that you don't have the luxury of moving it around all over the place. You have a petabyte of data split across 1,000 machines. Each has a terabyte. You can't be shuffling that around the network. So you have to ship your computation to where the data sits. That's problem number one. You have to serialize your computation, know where the data that this little part of your computation acts on sits, ship it there, run it there, return the results. How do you deal with failures? These are commodity machines. They are, by definition, low quality. They will fail. Their hard disks are sometimes mechanical. They just have mechanical parts that fail. There are so many failures you have to deal with. Your computation is not done when the last machine is done. So you have to wait for the last machine to finish, which means you have to figure out how to design your algorithm such that the very last machine finishes as fast as possible. You know that Ethernet networking is not fast, and worst of all, you would have to write algorithms for every type of machine and processor in your cluster. So you have to write one program for the master algorithm that manages all the minions. You have to write an algorithm for the minion machine, and then you have to write another type of algorithm if you have many minion machines. So all this, from for people who are used to dealing with MATLAB and just writing a simple text file to get a computer to do very complicated things, is a nuisance. And so tools have developed to let people talk at the level of MATLAB to a cluster. And so this network, traditional network programming, is actually rarely used in a commodity cluster. So around 10 years ago, data flow models became very popular, the first one of which was MapReduce. Data flow models solve all of the problems that I mentioned for you in return for removing a little bit of expressibility from your programming language. So in the same way that we went from assembly language to C, which talks about if statements and for loops, we lost gotos, but we obtained a lot of ease of programming. In the same vein, we now give up a little bit of expressibility in our programming, but then gain the solution to all of the other problems that we mentioned in the previous slide. So MapReduce is the first one. If you're an ICME student or you've taken ICME, any questions from me, don't put your hands up. Who here has seen MapReduce? Okay, so for the guests, it's a fairly new thing. MapReduce came out of Google. It let Google index the web and solve all kinds of other problems. Nowadays, MapReduce has been replaced with newer tools like Spark and TensorFlow. I'm going to go into Spark because that's what I work on. TensorFlow, that's what I work on at Databricks. TensorFlow, actually, we use it at my company. And that's a slightly newer generation of a mathematical data flow language, I guess. So we'll go into Spark in a second. TensorFlow lets you define your computation as series of operations on tensors. Tensors are higher level matrices. And then that tensor will have some distribution capability, and it also has automatic differentiation capability, so that you can get a gradient out of your entire program, and then that gradient can be used to optimize parameters in your program. That's a high-level definition of TensorFlow. I'm happy to talk to you more about that. Spark, which I'm going to go into deep, gives you a resilient distributed data set, which is basically a vector that is distributed across the cluster. So you're all used to programming with vectors. Every one of you has probably touched the programming language sometime in your life, and you did it by, you had access to some vectors, you would manipulate items in those vectors, and those vectors were always sitting on the RAM of your machine. Spark gives you a vector that is distributed across machines. You can't do everything that you can do with a regular vector with it because that'd be asking for too much. You can do most things, and these things know how to rebuild themselves. So that if one machine goes down, then that part the part of an RDD that was sitting on that machine can be rebuilt. And there's nothing particularly interesting about that idea that is tied to a programming language, right? All programming languages have vectors, and so all programming languages provide an RDD, most programming languages provide an RDD capability. So actually, we do all of our work in Scala when we build Spark, and we provide bindings for Java, Python, and R so that you can call this distributed array in your favorite programming language. I don't want to go into the example of the RDD because that's a little bit too technical, but here is, the slides I believe will be shared, and in this slide we have an example of how to use an RDD. This here, just the RDD contains error messages, and we're going through finding the error messages and splitting them by tab, and we're using the full power of a cluster to do that. So using this basic idea of an array, which is a very powerful one, we've gone and built out many, many different algorithms, most of which are machine learning algorithms, okay? So I care about distributed computing in general. It so happens that one of the biggest use cases for distributed computing these days is machine learning. And so the MLlib library inside Spark has all of these algorithms in it. Most recently, we added neural networks. I see some neural networks in the posters back there. So actually, we teach Spark in my class, distributed algorithms and optimization. I see many of the students here. So probably a lot of them are using it for their projects. So go and ask them about it. We have we have all of the vanilla machine learning algorithms you can expect. And they all scale in different ways. There are three different ways that many of them scale. The first one is data size. So if you have a lot of data, this data sitting in RDD, you can come to us and we will train a model that the model is often small then off all of your data. Then there's model size. So if you have very large models, in the case of say a matrix factorization or a very large neural network, you can train with Spark, having your model chopped up between many machines. Not all of the algorithms that I mentioned on the previous slide have model scaling. Actually, most of them don't. So only a few of them have model scaling, and that's where we're building towards. So model scaling is something that we need to work on quite a bit. And then there's the obvious one where you have a cluster at your disposal. You have a little bit of data and you want to train a small model, but you don't quite know the parameters of the model, the hyperparameters, the parameters that the human must set. And so you would like to try a lot of different values. So you go and use a cluster for that. And we've built out basic linear algebra using these basic arrays. So here I put up a link to a paper that we recently put up. It will be presented at KDD 2016. And we have a linear algebra library in Spark. It will let you solve linear programs and variants thereof using your cluster. This is very powerful for those of you who are traditional MATLAB engineers. You probably solved a lot of linear programs in your MATLAB code. And so this is now possible with a cluster. So at Stanford, there are two things that relate to this. First is my class, Distributed Algorithms and Optimization, which we start from the fundamentals of distributed programming and then go up all the way to some non-trivial algorithms that are cutting edge, implemented on a cluster. I'm also organizing a conference on this. Unfortunately, it just sold out, but if you want to attend, send me an email and we can make that happen. The thing that I'm betting my career on is that we'll always be asking this question. You know, even if we have quantum computers, we'll always be asking this question. If I give you many computers, how are you going to run your algorithm on all of them? So however fast a single machine gets, that's great. I hope that keeps going forever. But there'll always be one kind of machine that we're all using, and there'll always be this question of, what are you going to do when you put 10 of them together? What are you going to do when you put 100 of them together? That's what I focus on, and that's what I teach, I think, most of the fundamentals of in our class, and then we make them concrete with Spark.